So in this video, I am going to do an example of the Atwood machine calculation to find the acceleration. And I'll also do some free body diagrams, which are the last question on homework 3. So in this problem here, let's just say that mass 2 has a value of 2 kilograms, and that mass 1 has a value of 1 kilogram. I specifically made mass 2 larger. It doesn't have to be. You can make either one, either size. The math will actually all come out and it'll do what it's supposed to do, which is the nice thing about this equation here. So this is the equation we derived in the last video for the Atwood machine, the acceleration associated with the smaller mass, in this case m1. It's going to be positive, it's going to be upward. m2 is going to be the negative value of this. Alright, so let's go ahead and calculate the acceleration of m1. It's going to be equal to g times 2 minus 1 divided by 2 plus 1. It's equal to, therefore, g times 1 divided by 3, or about 3.3 meters per second squared. So m1 is going to accelerate upward at 3.3 meters per second squared, and m2 is going to accelerate downward at 3.3 meters per second squared. That's what this equation tells us for these masses. Again, it's kind of like a plug-and-play sort of problem at this point. Once we have the derivation, we just need to know which equation to apply in this case, which is this one. One thing that is in the homework, I think, or in the next homework, is where I make one of these masses really small and the other one really big, kind of like what we did in the hanging block problem. So let's think about it in this case here. Let's arbitrarily make m2 incredibly big and m1 very small. So in the limit where m1 is very small and m2 is very big, I would have that the acceleration is equal to g times m2 divided by m2, or g. In other words, m1 would accelerate upward at g, and m2 would accelerate downward at g, as if it were in free fall, which essentially it would be. If m1 became incredibly small compared to m2, then m2 would effectively be in free fall, and this end of the rope would just be flying upward at the same acceleration that the other one would be free falling. Okay, and I could do the other extreme. I could say let's make m1 very big and m2 very small. So if m1 were very big, then this would look like a negative big value divided by a positive same big value, with that being very small. So m1 would have then the negative acceleration downward, and m2 would have the positive acceleration upward. And m1, if it were much bigger than m2, it would accelerate downward at g, and m2 would accelerate upward at g. So I like playing thought games with making one object really small, the other one really big, to see what we're going to get. It's a nice way to think about the problem, and it's in the extreme cases. Okay, so that's the Atwood machine. I want to spend just a couple of minutes talking about free body diagrams and how you can draw them in a few cases, particularly for when you're jumping out of an airplane. Let's say you're parachuting, like I showed you in that video way earlier in the semester. So basically, if you're jumping out of a plane here, we haven't talked about this too much. The other problems regarding the free body diagrams are consistent with what we've talked about. So I don't necessarily need to repeat those, although I'm happy to answer questions about them if you have any. But let's just think about somebody jumping out of an airplane. And so we can think about the concept of air resistance. So when somebody jumps out here and they're falling downward, accelerating downward, I should say, at first there really isn't any air resistance. Air resistance comes up when they start moving really quickly, which they will eventually move very quickly if they're just jumping out of an airplane. In just a few seconds they'll be moving so quickly they'll feel a lot of air resistance. It'll be like the wind is just blowing past them really quickly. And that offers a force in the upward direction. But when they first jump out, they're basically completely in free fall. The only force acting on them is gravity. That would be the free body diagram. After a short time that they've been jumping, gravity is still going to be acting on them, but then you're going to start to get some air resistance because they're moving faster and faster. And as they continue to fall, they'll reach a point where they'll still have gravity acting on them. I should write gravity here. But the force of air resistance gets bigger and bigger the faster they go, until at some point it equals the force of gravity. And that's a case called terminal velocity. Notice that the same force up is equal to the force down. And that means that they're not accelerating anymore, but they are moving at a very fast velocity. So they're still falling, but they're not falling faster and faster and faster. So that's the case of what happens when you're jumping from an airplane. And of course, at some point when you jump from an airplane, your parachute's going to open up, and you're going to be continuing to fall downward. Whoops. But your terminal velocity would have gotten much lower, which is what you want. You don't want to hit the ground moving at 110 miles an hour, which would be the case here. So the parachute opens up, and that slows the rate at which you're falling. But you're still falling, but in this case, you still have a terminal velocity, air resistance, which is just bigger than it was over there, and Fg. And so this is going to be, this air resistance, well, it's actually going to be equal to Fg, but it's going to be equal to it at a much smaller velocity with the parachute open than in this case over here. And then when you hit the ground, let's think about what happens. It's the same thing as the jumping problem, the jumping and landing problem. When you're leaving the ground or when you're hitting the ground, the upward normal force is going to be bigger than the force due to gravity. So if you've ever jumped down, as we talked about, you want to be careful of your knees because you feel that really big upward force that can be dangerous to your knees. So when you're landing onto the ground, whether you're in a parachute or whatever have you, when you're actually coming to touch the ground, I'll just draw one of these guys here. You always have the force due to gravity because we're on the Earth, so we're always going to have that. But as you're touching the ground, you're going to experience a really big normal force, just for a moment, kind of like in the elevator problem. Really big upward normal force when you're coming down to the ground or when you're starting to accelerate upward. Same thing as the jumping problem too. Big normal force when you're starting to jump up or when you're just coming back down from having jumped. Gravity will always stay the same, force of gravity on you, but that normal force will be big. And then once you've landed, gravity and the normal force should then be the same because you're no longer accelerating. So keep that in mind as you think about free body diagrams. There's a few on the homework, and there'll be a few on the first exam, which is going to take place on Thursday, starting at 10, just as if we were here for the regular semester. So I'll spend a chunk of Thursday reviewing what we've talked about so far this semester. And there is a lab quiz later today. It's a multiple choice. I'll have it on iLearn under the class, and I'll make it very obvious. Okay, so this is the completion of the very first set of lectures that go with what would have been Monday's class. I should have said the exam opens Wednesday after class. Sorry, not Thursday after class. So this is the completion of the lectures for Monday's class, and I will see you again on Wednesday, or you'll see me in any case. And I'm also open to questions on Monday or Wednesday during class, or if you just want to email me at any time, that's okay also. All right, take care. I hope you're doing well, staying healthy. Bye-bye.